Fine. Okay, it's a pleasure today to have Vincenzo Vitelli from Lorenz Institute in Leiden. Vincenzo got his degree at Harvard, and then I think was a postdoc at Penn. I think so because during that time he was here, he wrote papers at Chicago, he was sort of all over the place, running around. And his thesis work was on liquid crystals, and since then he's been involved in all sorts of problems relating to topology, topological defects, things like that in condensed matter physics. You guys may remember last year or last term, Charlie Kane came and gave us a talk on topological insulators and their classical analogs. Like a couple days after that talk, I called him up and he said, "Oh, you have to see what Vincenzo's done based on that." Okay, and I heard him talk, and it was amazing, especially because they were toys to pass around. So Vincenzo's going to tell us about topological metamaterials.
Yep. Well, thank you very much for the opportunity to present my work here. Indeed, I'm going to illustrate what the topic is all about using a simple demonstration based on Legos. But I would like to start by explaining exactly what we mean by topological metamaterials, which appears to be a rather bombastic name for just assembling some Lego pieces on a line. So I want to first start by saying what a metamaterial is, what this term usually designates. So typically by metamaterial, one designates a structure which has some peculiar mechanical properties. For example, the way it responds to applied deformation, applied stresses, like this origami structure. But the peculiar thing about the structures is that whatever properties they have, they stem from the geometry of how the pieces are put together and not by the chemical compositions of the constitutive components. Okay? So, for example, here you can illustrate the peculiar response of this origami structure simply by looking how the pieces have been put together in essentially hard cardboard model. And one of the things that is peculiar is the ability to essentially absorb the compression that you apply by means of folding mechanisms, okay, that allow you to screen the presence of strains in the structures. Similar things I've done also using metamaterials that rely on buckling. In this buckling structure, for example, by applying a compression, the whole structure buckles and can absorb, can acquire some very specific property in terms of how it transmits sound. A third application I want to bring to your attention and spend maybe a touch more time to just give you a sense of what you can actually do with these structures stems from some work that we've done with Michelle Driscoll, who is in the audience, who was in the Nagel lab. The idea here was to change some geometric parameters of a structure like this, which is just made of plastic on a honeycomb lattice. And we wanted to demonstrate that you can actually tune the way a material fails by just changing the geometric parameters. What we did was the following. Actually, Michelle is the person who certainly did the experiment. She took this structure, and when you make this honeycomb lattice with a very high ratio of width, sort of thickness over length, so very thick beams, then this material, once you pull on it, breaks in the way you would expect. A succession of bonds break, you form a crack, there is a lot of stress here. But if you make the same structure with very thin beams, such that the bending elasticity, which are additional constraints for the material, are no longer relevant, then this structure no longer breaks by catastrophic failure by means of cracks, but rather you have isolated bond breaking in an apparently random succession. The way this works, this change in failure behavior, is because, again, as you saw in the movie up there, once you compress on one of those, once you pull on one of those structures, the stress that you apply at the boundary is not congruent with what happens inside the material. The material, instead of stretching the bonds, can use one of these folding mechanisms in order to screen the applied perturbation, and hence it does not break. Okay? All of this is tuned by geometry. Okay? So this is just a bunch of examples. But what they have in common is that in order to understand how these things work, you have to understand a concept that the engineer call a mechanism. Namely, you want to analyze a mechanical structure and identifies those motions that exist that cost zero stretching energy of the basic components. A very familiar example that you might have played around when you were a kid, it's a pantograph. No? Here, there is clearly a motion of this structure that does not stretch any of these rods. One aspect to keep in mind is that this motion, despite physicists often refer to it as a zero energy mode, is not a standard vibrational mode because it does not have a characteristic timescale that you rattle back and forward. Rather, it's a direction in phase space in which you can move at zero energy cost. Okay? And so part of this talk will all about studying a system like this, in which you have a bunch of components, and you want to study their motion subject to constraints applied to it. Okay? If you ask yourself the question, of course, these mechanisms are at the heart also of robotic structures. In fact, if you put a motor, then you can activate a mechanism, and then you have the building block of robots or other actuated structure. Now, the standard way of figuring out whether or not you have the zero energy modes or mechanisms goes all the way back to Maxwell, and probably Charlie and Mathieu or others that will have given a number of talks on this topic here. The idea is very simple. You count the number of degrees of freedom, you subtract the number of constraints, and the difference between the two gives you the number of zero modes, or the number of these under constrained motions. Now, despite this criteria seems so simple, there is already a little detail which is hidden in the very definition of constraints. This would be true only if the constraints were independent. If some constraints are redundant, clearly we are overcounting. If you eliminate if you want to keep here the total number of constraints and not just the independent one, then you have to subtract something on the other side. These objects are the number of redundant constraints that are useless in order to kill motion. Okay? Once you look at the results, you have that the number of zero modes minus the number of these redundant constraints, which the engineer calls states of self-stress, is equal to the degrees of freedom minus the number of constraints which are these rods. Now, one thing to notice about this construct is that this has the form of an index theorem in the following sense. Once you fix a structure like this, in terms of its connectivity, that is to say, you don't break any of these rods, then the left-hand side of this equation is fixed. That means that you can start to smoothly deform the length of these rods, for example, but you will never change the difference between these two numbers. Okay? So there's something invariant in that construct. Okay? The first time I saw this, from Tom Lubansky actually, I thought, well, the zero mode, I know what they are. The state of self-stress seemed useless to me. They seemed like redundant bonds, something that I could neglect. In the course of this talk, I want to show you how these quantities come to life by means of a number of experiments that probe their existence in terms of their nonlinear behavior. So be a little bit patient if you don't see immediately where I'm going with this. The one thing I wanted to ask is that if you could please interrupt this talk if there's something that doesn't make sense or you don't like, it would be more useful to have a good, to get going.
Sir, can you say again why you look for motions that have zero stretching energy? Because it seems like the stretching energy would be like some sort of higher order terms in the equations of motion, so it might be important.
Yeah, so actually what we are looking for is to use these motions that don't cost any stretching energy to make materials that have peculiar properties. So we're deliberately looking for them. Okay? Now, this is what, so I just told you a little bit what a metamaterial is, how a metamaterial relies on the presence of easy direction in phase space where you can move without paying an elastic cost. Now I want to tell you a little bit what a topological material actually is. A topological material, and of course here this is not a material, it's just the head of a baby. It's a structure that relies on the presence of topological invariants. And to give you an example of what a topological invariant is, which connects to the index theorem that I just shown you on the previous page, I want to give you this example. You all know that if you try to comb the hair on a sphere, on your head, or if you like, you draw a vector field on a sphere, it's not possible to do so without putting some singularities, some place where the field must vanish, like this point on the head of this baby. Okay? In particular, on a sphere, you know that there must be at least two of these points. The statement, which is a bit more precise, is that the sum of these points like this, which look like vortex, and the negative counterpart of it, the difference between the two must be equal to the integral of the Gaussian curvature of the surface over you're drawing this vector field. Okay? So, for example, on a sphere, the Gaussian curvature here, it's 1 over r squared. When you integrate over the whole sphere, you get 4 pi r squared times 1 r squared. You divide by 2 pi, you get 2. And that tells you that there must be two of these guys, which are at the north or south pole, for example, unless you have defects with the opposite sign.
Why is the one on the right the opposite sign from the one on the left? Do you think you just reverse all the arrows from the one on the left to get the one on the right?
No. Actually, this is important. They're not classified according to the flux, as you do in electrostatics. They're classified according to their curl, which means that if you go around, you ask, how does the vector rotate as you go around? Here it goes around by 2 pi, here by minus 2 pi. Okay, so I'm being a bit quick.
You go around counterclockwise, say, in both of them, and you get the opposite.
Yeah, exactly. So this is more precisely, is the index of the two vector fields. Okay? But the point I want to emphasize here is that this index depends only on the integral of the Gaussian curvature. Okay, I can deform an object as much as I like. In fact, in the end, when you take this integral, it only depends on the number of holes. That means that as far as this right-hand side is concerned, you could take an object which has the shape of a cup, and this is a standard thing that you've probably seen before, deform it into a torus, and this quantity would not change, and as a result of that, the sum between these two things will not change. Exactly as the number of zero modes minus the number of self-stress does not change as you deform the geometry of the constraints in the previous example. Both are examples of index theorems. Both, and here is something a touch subtle, rely on the fact that this is a global criteria. It's a criteria that extends throughout the system. Okay? You have to count all the constraints, all the zero modes, or all the positive defects, all the negative defects everywhere. Okay? But now you may ask a question, well, in a material, you always have a patch. You always have boundaries. What do you deal with that? So let's take a little step more and move from the head of a baby to what is actually a real topological material built on this idea. Well, for example, instead of putting the hair of a baby on top of a sphere, why not considering a droplet with some liquid crystal molecules? If you have something like that, what you will observe is that you can still have this defect, and this liquid crystal, the number of these defects is again constrained by this geometry. Okay? This is just a simple physical realization of what you saw before. The molecules are playing the role of the direction of the hair. This, please.
It's not the same thing as an arrow.
There's a slight difference in the sense that in this system, you can also have defects which have index 1/2. Because as you pointed out, if you're one arrow, double arrow, there's a slight catch. Yes. It's also true that you can have a similar setup if you play with a crystal. For example, if you take a crystal on a curved substrate, this is something that was done by William Irwin and Paul Chaikin a couple of years ago. Even in a crystal, even if the crystal is not orientational order, but it's translational order, there's still an orientational order component. In particular, if you look at the defects in crystals, here is a point which is 5-fold coordination, and here is a point where it's 7-fold coordinated. There is a deficit of 2 pi over 6 in one case, and an extra 2 pi over 6 in the other, because the normal in the crystal would be to have an hexagon. Okay? So these two objects can be viewed as defect, exactly as the ones in the previous slides. And so one of the things that we were studying with Paul and William is would the integral of the Gaussian curvature on these surfaces that we're making in the lab be simply equal to the number of positive minus negative defects that you see over here? Notice there's an extra factor of 6 here that is coming because of the same reason that you were alluding before, namely the deficit in angle is not 2 pi, but it's 2 pi over 6. but the structure is exactly the same. Now, when we were doing this, William Irwin, who was checking as a routine check this formula, was a bit perplexed. Because when we were comparing the right-hand side with the left-hand side, on a patch, in particular, say, on a catenoid, you do it only in this part, we were finding that the left-hand side and the right-hand side were not equal unless we were adding an extra term. Okay? If you have a crystal on a whole sphere, it doesn't matter if you put extra rows, which are the defects typical of crystals. These are called dislocation. The reason why it doesn't matter is because dislocation are only defects that represent missing rows of atoms. They don't change the orientational order. However, if you are on a surface which has a boundary, then the game changes. Why? Because if you look at the core of a defect that involves a missing row of atom, here, you see that there is a 7 and a 5 orientational defect right next to each other, a dipole of them. That means, based also on your analogy with electrostatics, that if you have a boundary and you want to figure out the total charge, it's not only the single charges of the free defects, but you also have to take into account the polarization. In particular, if you have a little dipole of defect, which is the dislocation stranding in between the boundary out and in, then you have to take into account when you do this formula the part which is inside. To be more specific, if you're studying electrostatics and you want to know the total charge, you will both consider positive charges minus negative charges plus the flux of the polarization. In this system, there is a topological polarization that arises from the density of these dislocations. The peculiarity is that the dislocation doesn't have an angular character, but its gradient does. And hence, once you have an edge, you have to consider these objects as entering. One other thing that you can now ask is that if you go back to the Maxwell criteria that I indicated before about the counting degrees of freedom and constraint, that's also a global thing. What if you try to apply on a patch? There will be boundary, there will be edges. And hence, non-trivial, counterintuitive example can arise for the same reason why this guy arises, and for the same reason why in electrostatic the polarization is also important in determining the total charge. Okay? Now, this may sound a touch abstract, perhaps. So what I'm going to do, I'm going to show you some examples of this. The first example is inspired actually by this very nice work by Ken and Lubansky, which essentially derived the formula for this topological polarization in the context of zero modes and states of self-stress. Rather than going through the math in exact details, I want to just show you one structure that has it. Then we just look at it, and I tell you what's peculiar about it, and I'll try to explain intuitively how that arises. The structure is very simple. I'm going to pass around soon. It's composed of rotors with the balls attached. It's inspired by the molecule polyacetylene, by the way. So there is a rod here. Each of these rotors can pivot, as you saw, and they're staggered in this peculiar way and connected by springs. Okay? And now you can sort of see that there is a natural quantity in real space, which you can understand without fancy mathematics, which is the direction that all these rotors are pointing to, in this case all to the right. Okay? So this ground state corresponding to all the rotors pointing on the right. What Ken and Lubansky studied in this system is they asked the question, are there zero energy modes in this system? So there's a bunch of springs, so you can write down the dynamical matrix, and you look for zeros of that dynamical matrix. What they found is that there is none in the bulk, but they found one at the edge. Okay? And this state localized at the edge would be localized on the opposite edge if you constructed the system in such a way that all the rotors are pointing in the opposite direction. Okay? But the peculiar feature of this structure is that one of the two edges is singled out. Okay? In particular, notice one thing, that if you count the number of degrees of freedom and the number of constraints in the structure, you'll find number of degrees of freedom is 1, 2, 3, 4, 5, 6, 7, 8 rotors. The number of constraints is identical if you use periodic boundary condition. But the moment in which you cut, then there is an extra zero energy mode. And it gets localized at one of the edges. What is a bit surprising is that in terms of local constraint counting, the two edges are identical. Because here there's one rotor and one spring. Here there is one rotor and one spring. Why does it localize here and not here? That's because there is this quantity, this polarization, as I called it before, that singles out the edge. The second feature that is peculiar about this structure, it has an acoustic gap.
No, I just don't understand the localized mode is that there's some vibration on the right,
Right.
but it dies exponentially?
Absolutely. Yeah, and I'm going to tell you now also how it dies exponentially.
Okay.
So it's a vibrational mode with zero energy frequency. Sorry, with zero frequency. So it's a zero energy mode. So there's no restoring force. And there's an exponential decay inside the bulk.
So that just means that it's some other position, it just goes to some other position. It's zero frequency. Right?
Yeah, so it could be many things. It could mean that once you push on it, the higher order terms in the energy landscape restore it, or there could be some non-trivial motion. I'm going to show you what happens in a moment. You also anticipated the next point, namely that there is a localization length of this mode, represented by the amplitude of these green arrows, which tells you the direction, the polarization of vector of the mode, and is controlled by the inverse of this rest angle. So when this rest angle becomes zero, so the things are perpendicular, then the mode stretches throughout the sample, becomes extended. Okay? Now you may ask, what's happening at that special point? If you take this structure here has a gapped acoustic spectrum. What that means is that if you take up one of these particles here and you try to move it even infinitesimally, you'll have to pay a finite energy cost. Okay? This property, however, is absent if you change the geometry of this structure by making this angle equal to zero. Okay? So this structure is undergoing, if you like, a transition from a localized state when this angle is is non-vanishing, to a delocalized state when the angle is vanishing. Okay? Notice that this is the tunability that exists in this structure. But irrespective of the value of the angle, there will always be one end which is singled out over the other. So I want to emphasize the fact that the left versus the right is singled out is robust topologically. But the extension of the mode, it's tunable by changing the geometry of the structure. That's why this is a topological metamaterial. It has both features, the tunability that is achieved by closing the acoustic gap, and the stability, which is resulting from the presence of an invariant, which is this PT. Okay? Now, this may sound a little bit abstract or perhaps even difficult to see where you're going with it. When we learned about this, and we had also some of the questions that you had about what happens when you touch on this mode, we decided, why don't we build one of these things? And since the whole story is about zero energy mode, we figured we may as well forget about the springs and build it out of rigid rods. Because then, by definition, we know that we are isolating the manifold that costs zero stretching energy. All right? And here is the thing. This is the thing that Paul saw. So now I'm going to try to show you all these things that I said in words, just with this toy in my hand. The first thing is that, and since this is a bit small, I'm going to do it simultaneously also here. So first of all, replace the springs by rigid rods. So now everything will be rigid. This will be rigid, and that will be rigid too. Here it comes. Okay? And now you'll see the hand tries to move, and nothing moves. This means that since we made the spring constant infinitely large, we have pushed the acoustic gap of the structure to infinity. Every vibration associated with normal sounds is killed. Okay? If you don't believe me, you can do it yourself, because I'm going to pass these guys around. Please be careful because they're a bit distracting. Especially Paul has been. Okay. Okay, but then let's try to see the second thing that we were talking about. I said that there was a vibrational mode at the edge. How does that work? Well, here it comes. You see here, there's something swinging left and right. But notice, if I go here, it doesn't move. Okay? So this is, in essence, the object that Charlie and Tom were predicting as analog of an edge state in electronic systems, localized at the edge of the sample. Now, this looks like very little, but when we started asking a question, this is a zero-energy mode, and it's a phononic system. In an electronic system, you can push on an electron, you get an electron to move, without necessarily moving the underlying structure. But with phonons represent the stateful motion of the underlying structure. So our question was, if this is a zero-energy state, and you touch on it, what happens? Can you actually get these states to propagate from the left to the right of the structure? And this I'm going to show it to you just simply here. I'm going to apply a little tilt and see what happens. This moves. Okay? So this motion that you're seeing is not captured by linear elastic analysis because evidently it's not a small deformation. And moreover, in this system, a small deformation doesn't exist because there's zero energy restoring, there's zero forces restoring it. If you want to see how it happens here on the screen, well, here first is the conclusion that you have in linear theory. Mechanical energy cannot be transmitted by linear vibrational modes. You saw it before because they're localized on one edge. But then, if you ask what happens in the nonlinear regime, this is dead, I think. Do you have another one? Oh. No, actually, I think it's sporadic.
Pointer. There's a pointer there.
You mean the mechanical one?
In the box.
Okay. Yeah. And so, if you ask what happens, that means that also this is not working now. Okay. What happens when we excite the mode? This is what I showed you just now. You see the motion that we were discussing. Okay? And this motion is just at the bottom of a Mexican hat potential. Okay? And so one of the things that we wanted to understand is that how can we make sense of this motion? This motion is a bit like you try to push on the edge mode, and the edge pushes inside the material. Okay? So let's take a look at it more carefully. It seems that within nonlinear theory, or rather what happens whenever you excite this mode, something that looked like an insulator with exponentially localized states at the edge is becoming a conductor via nonlinear objects, which are presumably solitons. So,
Is more robust if you perturb the lengths of the bursts?
Yes, fairly. In fact,
That's probably what's happening in the toys. It's not, they're not all exactly the same.
absolutely. Within some range, because clearly if you cut one of them, then you have two different systems. Okay? But there's some more peculiar property of that motion that I'm going to review. The first thing that one may want to ask. Sorry, I didn't hear.
What sets the speed?
Very good. In a nonlinear, if this is a nonlinear wave, the speed is not set by the square root of an elastic parameter like in linear sound, but by the amplitude of the perturbation that you apply. That's why it's a solitary wave and not linear sound. Okay?
So if I push it harder, it goes faster?
Yeah, and if you don't push at all, if you push just a bit, it stops. But it's even more peculiar than that, as I'm going to show you here. The first question we can ask is that, how does it get to move? What is the mechanism of propagation? Because this structure, as I illustrated, is gapped in the bulk. Nothing moves. So how does this guy get to move to one end to the other? Well, you can sort of see here, and I'm going to show you before. You see, Mark, I have to keep pushing. If I don't push, it doesn't move. But once you make him move, notice that this is probably the most peculiar thing about the whole talk. If you look at this thing here, you have a domain wall. On the right-hand side, on this side, they're pushing like this. The rotors are pointing like this. On this side, they are pointing like that. And the edges, which are under-coordinated, are rigid. And yet, the domain wall, which has a higher local coordination of them, has, on the other hand, a zero mode trapped there. So the way this moves is that you excite the zero mode makes a domain wall, the domain wall slides. And that's how it works. Okay? But notice you have to push right at the domain wall. Anywhere else, the structure is rigid, and this will not be able to move. And it can only move if you start like this, it can only be excited, this motion, from one edge and not the other. If I hit here, nothing happens. Whereas if I hit here, then this guy can move. If you didn't follow it here, I'm going to show it on the slide. You see this domain wall moving progressively. Is working? Oh, okay, thanks. Working throughout. So why am I making a big fuss about this domain wall? Here I hope that if I lost you when I was going through these talks about the polarization, I can get you back. The domain wall, maybe not with that. There's a signature in real space, which is this direction of the rotor. This direction of the rotor is the signal in real space of the polarization that I was talking about. The topological polarization that tells you whether this state can be present or not. Notice that at this domain wall, there is a flux of the polarization inward. Okay? It's the presence of this inward flux of the polarization that enables a zero energy motion to exist, even if by local constraints there's no reason to expect it there. Okay? So if you look at this and you may say, well, okay, it's a lot of words, but if I look at that toy, it seems pretty much like an Ising model. What I'm calling left and right orientation of this rotor is like spin up and spin down. And this is just a domain wall moving in an Ising model. No, not really. For a number of reasons. The most important of them is that in an Ising model, if you put a domain wall in it, it will never cost zero energy. It will always have a finite energy cost. And moreover, in an Ising model, there's no reason why a domain wall can propagate from left to right and not from right to left. There's nothing that breaks the left-right symmetry in that model. But in this structure, we know that this domain wall exists without stretching any of the bonds. So the elastic energy is zero throughout this motion. And this is the peculiar property of this. I want to show you how... That's the point. You cannot have two of them. The standard thing that you do with soliton, for example, with hanging pendulum, that you make one coming from here and one coming from there and they go through, cannot happen here because this is a one-way channel. Okay? I'm going to illustrate it to you, how it comes about.
Or you can have something only to the right of the right pointing polarization.
Yes. And so now the question that your intuitive question points to is, how does the field theory that presumably describes this simple toy differ from the normal double well field theory? And this is what I'm going to go next. Okay. So, rather than plunging into derivation, let's just think phenomenologically. What do we expect? Well, we said that it looked a bit like the Ising model because you have two ground states pointing to the right, which is what you see here, or pointing to the left. Okay? So if you define the projection as r sine theta x, so this is the projection, then you have a natural order parameter. So you will have a series of terms in this Lagrangian density. One is a kinetic term. Forget about it for the moment. This one here is the normal elastic term. That is the gradient of the order parameter squared, which is also existent in the Landau-Ginzburg theory of magnetism, for example. This one here is the phi to the fourth potential. If these were the only two terms present, the kink will always cost a finite amount of energy. However, in this structure, in this model, there is an extra term whose presence I want to emphasize. This extra term, it's what I would call a topological boundary term. And you can guess its existence without doing any mathematics, simply because you know from counting the number of degrees of freedom and knowing that there's 1 degree of freedom more than constraints, that there must be a zero energy motion. That means that whatever integrand of this field theory you write, no matter how nonlinear it is, you should be able to cast it as the square of something. Or rather, if you can cast it as the square of something, all of these terms, then you can make sure that there is a non-uniform field that represents the solution of this integrand. And once the field is satisfying this differential equation, then you know that that deformation will cost zero energy. So in other words, you need the topological boundary term here to complete the square. Once you complete the square, something that sometimes in high energy theory is called BPS trick. Once you complete the square, you now can essentially notice a number of things. The first one is that the term that I had to put in order to have a zero energy motion, manifestly breaks the left-right symmetry. Okay? So now you know why the motion can be initiated from one end and not from the other. But this term is also a boundary term. So it does not change the equation of motion once the things start moving inside. Okay? And so ensure zero stretching energy. So if you like, if you're a phenomenologist, you could guess the presence of that term up to the prefactor, simply based on the notion that you want to put you know that the zero energy motion has to exist. The other thing that it does is breaks the left-right symmetry, but it does also another thing. Since you pick up a sign here, you notice immediately that it allows you to have kink solution, like this one here, okay? But it does not allow you to have the anti-kink, okay? Because the anti-kink solution will correspond to a plus sign there, okay? So this term is what is not present in the Ising model. Okay? There is an interesting side story here on how you can use supersymmetry, actually, to elaborate on this consideration. But I think it's probably less intuitive than the rest of the stuff I want to show you. So this is the kink that we're talking about. This is the moving domain wall between the two different polarizations. Now, you may ask, okay, this is a kink. What sets the width of the kink? The width of the kink is set by this angle. In other words, by how close you are to the point in the geometry of the structure where the acoustic gap is closed. So remember in phase transition, for example, in critical phenomena, you can get a diverging length scale at Tc. How does that originate? It originates from the vanishing mass term of your field theory. Here, the vanishing mass term of your field theory is controlled by the distance from the gap. So when you close the gap, the width of this domain wall diverges in the same way as the width between magnetic domain wall diverges when you are at Tc. Okay? So there's an underlying phase transition associated with closing the gap that we are exploiting to tune the property of these acoustic solitons that propagate. Okay? Now, one question you may ask is that, well, okay, what about the anti-kink? We said it doesn't exist, but why it doesn't exist? Well, intuitively, you can sort of see why it doesn't exist. You take this and you look at it and you say, well, if I want to, instead of having this guy pointing, this pointing in, I want them to point out, what I would have to do is to take this rod that are now pointing in and make them go out. But you can clearly see that it's impossible to do that because you would have to put this structure under stress, which you cannot do if these things are rigid. Okay? So the anti-kink, which is the opposite flux of the topological polarization, corresponds to a state of stress. Okay? And you remember that we had started this discussion by saying number of degrees of freedom minus number of constraint is the number of zero modes minus the number of self-stresses. We were saying the states of self-stresses are like assignment of tensions in the bonds that are redundant, so they do not result in displacement of the nodes. And this I told you, well, they're useless. Well, let's see if they're useless or whether there's something that you can use. What I'm going to show you here, it's another structure. which is a Kagome lattice of a peculiar type, which I think Charlie might have introduced in his colloquium a year ago. But the only thing I want to mention to you is that in this structure, you can create at the same time a domain wall where the polarization is pointing inwards, where you localize the zero modes, and also a domain wall where the polarization points outwards, where you can localize this propensity to sustain tensions, which is the state of self-stress. What I want to show you is how this redundant constraint that seem almost like a definitional issue that you don't need to worry about can actually be harnessed to tune the property of these materials, and in particular to control how they buckle under external loads. Okay? So here is the idea that we have. We take this peculiar lattice, here it comes, which has all this state of self-stress, that you should think of it in the same way as the zero mode is a propensity for motion. The state of self-stress is a propensity to store tension that cannot be relaxed by displacements. Okay, it's like a bomb that you're setting to explode. So we have all of them here, and now we stack a bunch of these lattices by connecting it also to the lower one in a way that doesn't change the fact that the number of constraints and degrees of freedom are exactly equal. Again, more, and then what we do is we make the structure. We take a 3D printer, and we make this stacked bunch of lattices, all of which have the self-stresses here. Okay? You say, well, okay, what have you achieved with that? You just piled up a lot of nothing. Well, it's a propensity for something. So in order to activate it, in the same way as you have to go in nonlinear theory to activate the zero energy mode, you have to also do something here. And the something you have to do is to take that structure, put it between two transparent pistons, and now what you're going to see is that we're going to push with the piston like in this direction, and at the same time, since the piston is transparent, we're going to look through it. Okay? And this region in red is the region where the states of self-stress have been localized. Notice that the states of self-stress are just little tiny geometrical variations that do not change the material parameter throughout the sample. But what I want to show you here is what happens where they're localized here if you compress the structure. Okay? If you compress the structure, you will see that the buckling deformation is entirely localized where the self-stress are. So the self-stress, exactly like the zero mode, can be used to sculpt inside the material a propensity to undergo a mechanical failure exactly where you want. Okay? And if you close the gap, the mechanical failure can spread throughout the sample. In a similar way to what Michel was exploring with Sinagel, but in that experiment, you are not closing the acoustic gap of the structure, but you are reducing the number of effective constraints, which is using like a jamming transition rather than a topological transition. One thing I want to tell you is that these structures, like the one-dimensional chain that I showed you, you can also construct it as you saw in 2 dimensions. And you could see here the whole idea was that you can find the motion in places where you do not expect, which coincides with domain walls. Okay, so domain walls are a simple type of defect, but in 2-dimensional lattices, you can have more complicated defects. You can have, in particular, dislocations, which are missing row of atoms. Okay? Now, what you're looking here, it's again a Kagome lattice, which is a lattice which is everywhere 4-fold coordinated, which is the magic number to ensure that the number of constraints and the number of degrees of freedom are exactly balanced. And what we're putting here is 2 dislocations, and you can view these dislocations as being objects in which the plaquette of this Kagome lattice has here a 7 and here a 5, and there's a dipole characteristic of the orientation of this defect. There's one here and there's one here. One thing I want to emphasize, if you look at this, is that everywhere in this lattice, the coordination number is the same. So from local consideration, nothing should move in here. Okay? And now the question that I ask you is, if you look at this, can you guess whether motion is possible or not in this lattice And where would you guess that to exist? And so we will redo the same game as we did with that simple toy, but with this more complicated structure. You will see a hand coming inside this movie here. So you see the hand of Jason Paulosa tries to move all the white triangles. So, and you notice that the system is rigid in the bulk, pretty much like this system was rigid in the bulk. Okay? You remember how this was rigid in the bulk?
Are they connected by little pivots or something?
Yes, so they're triangles connected by little pivots. And so at each pivot, there are two triangles coming out. So there's like 4, that's why I said it's 4-fold coordinated. And 4 is the magic number that ensures the bounds of constraints and degrees of freedom. Okay, so nothing moves in the regions that are white. What I want to show you, though, is that if you put a defect, as you had put the domain wall in here, then there can be motion localized at the defect, even if the coordination number is not lower there than anywhere else in the structure. But now there's a peculiarity, that this lattice allows to orient the defects in 2 different ways, depending on the dipole of the dislocation. So let's just do the experiment. And you see the hand will walk in again. Here it comes. So the hand will probe first this dislocation. Notice that there's a tiny motion localized right there. Okay? But if you move here, there's no motion, despite this object and this object are identical in terms of their local structure. Okay? So what's happening here? What's happening here is that the dislocation that moves has a zero energy mode trapped at it. So it's one of these topological modes localized there. The other one, on the other hand, has a state of self-stress. So these arrows are the polarization vector of the mode. And here, the bonds has the states of tensions. That is the one that we were exploiting before in order to induce the buckling. Okay? And the intriguing feature of the system is that whether you have a protected state of motion or a protected tension stored in your material depends on 2 quantities, each of which is a Berry phase. Let me tell you in more detail. Namely, in this material, exactly like in the one-dimensional chain, there is a topological polarization. The topological polarization is indicated by this arrow. And you can sort of see the sense of directionality in the lattice for the fact that this plaquette has a pointiness to them. Okay, so the polarization, it's oriented opposite as the nose of that pentagon. In order to define the polarization properly, you have to define topological invariant in the Brillouin zone. But besides the topological polarization, there is a second invariant, which is the topological charge of the dislocation, which is the Burger's vector. That is to say, the step that you're missing if you take a circuit around the dislocation. Or alternatively, in equal term, which is this dipolar structure. Depending on how this dipole or that dipole are oriented compared to the topological polarization, you can have this dot product to be either 1 or -1. When this dot product is +1, you have a zero mode. When this dot product is -1, you have a state of self-stress. What this dot product represents is the flux of this topological polarization at the dislocation center, where the dislocation center acts as an effective edge of the system. The peculiar thing, though, is that we can position these effective edges wherever we want inside this material. And the state of motion or stress will be protected because they rely on the product between 2 topological invariants. So in other words, if you want to get rid of the motion that exists here and turn it into a state of no motion, you have to unwire everything here. And so the reason why for us this is interesting is that it's as if you have made a topological punch card in which you can encode the desired location, a state of motion, which can then be activated by touching. You can store like a bit of information if you like. And all the states are, of course,
So just wondered, is the mode binary mode, are the parts moving?
so in this case, it cannot move across the sample because this is a zero energy mode which has a non-linear restoring force, unlike the previous one which was a whole soliton moving across. The reason of the difference is because in the toy, you remember when we counted the total number of degrees of freedom, there was one more than constraints. Whereas here, they're exactly balanced. So the reason why there's motion here is because there's a substrate there. So strictly speaking, in a finite sample, these guys are not strict zero energy mode. They are mid-gap states with a very small energy. Yes, so there could be systems where it goes around the edge, but not quite here. Yeah. So, well, I hope I convinced you that even in 2 dimension you can have this localization, topologically protected states. So let me try to draw some conclusion as to where we may be going with this, speculate a little bit rather than give you a detailed explanation. So we started this story inspired by polyacetylene. Polyacetylene it's a molecule that played a key role in molecular electronics. I think one of the things that Charlie and Tom achieved by introducing some of these systems is to create mechanical analogs of polyacetylenes that will display protected states not only on the electronics side, but also in the mechanics side. Okay, now, these states, however, as I try to argue with you, being zero energy states are not normal vibrational modes. They are vibrational modes. They are modes that can move only when activated by external forces. Okay, so they are the characteristic building block with which you can make, for example, robots or a moving mechanism once they are actuated. So one of the things that we're now in the process of doing is to activate this mechanism in a way that it's less pathetic than just touching them with your finger, although the idea is the same. And that will naturally get us towards robotics. For example, with the Lego pieces that you've seen, you can buy something called Lego Mindstorm and just stick in a robot, a motor. Kids are fond of it, and me too. But our dream, which at the moment is purely a dream, would be what if once we understand how to actuate this mechanism, how to put activity in it, we can take this logic back to the microscale where it came from. Not to do molecular electronic, but to perhaps design structures at a very small scales which have these protected mechanisms. Then we could be able to do perhaps something like molecular robotics. And at those scales, the fact that these mechanisms are protected by topology could be as useful as, for example, electronic states that are protected by topology for applications like quantum computers. Now, with this dream, let me conclude, and thank you for your attention.
More questions?
Can you explain more, in a little more details, what is the microscopics from which it came, this CH thing? What was the zero mode there? How is it observed?
Yeah, no, you can't. I mean, here was still. So this is really motivational in the sense that in this system there was an electronic state. So the system was an insulator electronically, but becomes a conductor because the electronic state couples to the domain wall in the underlying structure. So in this system, 1 degree of freedom is electronic, and the other degrees of freedom is phononic. So it's a bit different from here. Here you have, you see, if you look at this, you have the zero mode is a phononic degree of freedom living on top of a domain wall, and the two are coupled, but they live in this. They're both acoustic. Okay, so.
So precise microscopic analogs of this little toy, you don't know.
No, because in order to do a precise, what I mean by precise microscopic analog of this toy would be something in which this toy is made using nanoblocks.
Of course.
Yeah.
Isn't the optical fibers, the dark solitons, aren't they exactly what you're talking about in that case?
Not that I'm aware of.
Why not?
Because I'm not aware of any topological protection in those problems.
Well, they are topological solitons.
But I'm not aware.
Not the bright ones.
But I'm not aware, but may be wrong, of instances in which, for example, you can shine one in this direction but not in the other. Because this is the peculiar property here. This breaking of left rest.
Two of those.
Huh?
You cannot have two of those.
Yeah, exactly. That's the breaking of symmetry that you have here. Of course, there are many systems that support solids.
So when I was playing with the toy, there's a kink on one end, and you have to introduce the kink into the vault from that side. And once you have a kink like in the middle, it can move either way.
Mm-hmm.
Is there a way to engineer it so the kink can only move in one direction?
Yes. So what you have to do is to break also time reversal symmetry. Now, one trivial way is that if you put motors in there, and the motors rotate only in one direction, then you have what you want. Or the system must be made of components that break time reversal symmetry. That's one waveguide, essentially.
And so, like, you envision that this can be useful for something.
Well, if I should measure how convincing I've been from how you posed the question, I'm not terribly hopeful. Let me put it this way. Our motivation is not driven necessarily immediately by applications. What we wanted to demonstrate is that you can make topologically protect states in mechanics, that you can perform some very basic tasks, and that you can prime the response of these elastic materials in ways which are unexpected using this principle.
For example, you gave this example where it breaks if it is to break in a predestined.
Yeah, right, the buckling.
Like maybe it's useful, right?
Yeah.
If you take spaghetti, it will break in a random place, but
Yeah.
you put it there, it breaks
Yeah,
exactly in half.
But most crucial is that it breaks, it buckles in a region where there is no local propensity. There's nothing local that tells you that it has to buckle there. So you see, I agree, we haven't really produced your new screen for the computer will not break. But reflect upon this. You could imagine that you could break preferentially in one part because you make that part, say, different in terms of mechanical properties, for example, a different material. Or you could engineer the whole geometry on the material in such a way that it focuses stress preferentially in that part. Trying to find the criteria of how that is done, decoupled by variation in the mechanical strength of the material, is in itself an interesting task, because then you can tune materials in multiple ways and not relying on changing the material properties. This fact also that these features are very robust under smooth deformation of the structure is also something that could be potentially useful. I must also say the mathematical analysis of these things is also quite interesting, and perhaps an aspect that I've not overemphasized.
Okay, I think we should thank you.
Thank you.
There's wine and cheese upstairs. And he probably wants to